Hello everyone. Today I will present our work on 28 GHz channel measurements in the Cosmos testbed deployment area. This work was completed in collaboration with Nokia Bell Labs and the Universidad Técnica Federico Santa Maria. Next generation wireless networks such as 5G will utilize millimeter wave frequencies as enablers of increased data rates. However, the large path loss at millimeter wave frequencies requires the use of accurate channel models and measurements for different deployment sites. To meet this need, we conducted an extensive millimeter wave measurement campaign consisting of over 2,800 links on 24 different sidewalks in the Cosmos testbed deployment area in West Harlem. From these measurements, we can investigate important characteristics of the wireless channel, including the path loss and angular spread. As a bit of background on our measurement area, Cosmos is an open-access wireless research testbed that is currently being deployed in a 1 square mile area north of the Morningside Heights campus. Cosmos is a joint project involving Columbia, along with institutions such as Rutgers, CCNY, IBM, and Silicon Harlem. The measurement platform we've used is a custom-built 28 GHz narrowband channel sounder. The transmitter is equipped with an omnidirectional antenna, and the receiver's directional horn antenna rotates at around 120 RPM. We can record power measurements at 740 samples per second using a remotely controlled Raspberry Pi on the receiver. The receiver's spinning horn antenna means that we are able to record power in all directions. We conducted our measurements from 4 different locations. 3 are shown on the map to the left. These are the intersection of Amsterdam Avenue and 120th Street, the Columbia Law School Bridge overlooking Amsterdam Avenue, and the Faculty House overlooking Morningside Drive. We also took measurements from the Jerome L. Green building on the Manhattanville campus. This is shown in the map on the right. These measurement sites are quite representative of cities located in the northeastern United States. The plot shown here is showing the path loss as a function of link distance. The different colors represent different locations, and furthermore, we split the Jerome L. Green and the Amsterdam 120th intersection measurements into line of sight and non-line of sight. We can find similarities between locations and also some clear differences, such as those between line of sight and non-line of sight streets. However, the majority of our results lie within the line of sight and non-line of sight models provided by 3GPP. These plots show the impact of 3 different effects which we measured. The first is swapping the transmitter and receiver. The second is raising the height of the transmitter. And the third is measurements between different seasons. We find that the first 2 of these effects don't really have a significant impact, but measurements between different seasons do. And this is likely caused by effects such as the tree foliage, which, when there are no trees, there's less blockage, and we can see that effect in our measurements. We used our measurement results to perform simulation of expected signal-to-noise ratio values at streets around the Amsterdam and 120th Street intersection. We find that up to a 160-meter link distance, there is a sufficient coverage for over 15 decibels of signal-to-noise ratio, even in the streets which are not in line of sight. This signal-to-noise ratio is suitable for gigabit data rates at bandwidths that are available in millimeter wave communications. Our current work is conducting further measurements. In particular, we are currently investigating outdoor to indoor measurements, meaning that we have the receiver located indoors and we are moving the transmitter on the street. We are also interested in understanding the effect of sidewalk clutter, such as trees, parked cars, and lampposts. Thirdly, we are also looking into how to leverage our measurement data in the development of improved algorithms for antenna beamforming and network scheduling. Thank you very much for your time today.